and all participants today, and welcome to the second day of the uh, online mathematics, international mathematics camp or limit camp. And today our presenter will be Mr. Soham Bakshi, who is a third year BMath honors student. His interests are on analysis and geometry, and what he will be presenting is on the lecture of uh, sets of points of continuity, and some important notes that uh, the lecture would be for 1 hour to 1.5 hours, and after that we will be having a session of question and answer where you will be allowed to ask questions and the lecturer will answer. Please do silent your microphones during the lecture. Thank you, and let's proceed to the lecture then.
Okay. Hello everyone, and thank you, Ankan, for the introduction. Can anyone please confirm if I am audible and if the screen is visible?
Yeah, you are audible.
Okay, so I will just share the screen. Is it visible?
Yeah.
Okay, great. So I will turn off the video because it's not really necessary. And okay, so today we are going to discuss about sets of points of continuity. So by that, what I mean is the points at which the function is continuous. So a function, what is a function? A function is a function, like there should be a codomain and a domain, right? So a function from a particular set to another set, and then we need to talk about continuity of that function, and then we can talk about the points at which the function is continuous. Okay, so where I'm reaching is what the main important focus will be on treating with metric spaces. So I'm assuming the knowledge of metric spaces because that was included in the syllabus from what I know. So yeah, so basically we'll be taking functions from a metric space to another metric space. For now we can stick to reals. So a function from a metric space X to the set of real numbers R. And now we can talk about continuity of a function, of that function F, right? Like at which points is continuous and at which points is not continuous. Yeah, so just to briefly, like if somebody is here who is not comfortable with the notion of metric spaces, it is just a space where you can talk about distance between 2 points. And from that you can go on defining sequences, limits, and so on. And of course, you can also define continuity and stuff. So if you can't really understand what is going on with metric spaces, just think of something like reals or a subset of real. Okay, that is a metric space you know about, and the distance is considered to be mod of x minus y. So this is just a basic, like the idea behind what we are going to do. And then our interest is on the set of points of continuity of that function, and what kind of set can appear as a set of points of continuity of functions from a metric space to the set of reals. We'll shortly see how the questions arrive and how we tackle with them. And on to discuss about extensions. There is a very famous theorem in topological that, and some variations of them when we are talking about this. So we look into all that, but that will depend on how much time we have left. Yeah, so I think I can start. And of course, and there is a question and answer session at the last, but even if you are having any doubt in between, feel free to just unmute yourself and ask. That will be good for me also. I will understand how much communication is there in between us. Yeah. So yeah, so let me get started. So let's first see what are the basic questions. So let me ask you this. Is there a function f from R to R which is continuous on irrationals and discontinuous on the rationals? So this function should be continuous at all the irrationals, okay, and discontinuous at all the rationals. So at any point p by q, if like p by q natural, and at that point the function will be discontinuous. But at all the other irrational numbers, the function will be continuous. So can you construct any function satisfying this particular property? And there is a function like that. Is the famous Thomas function, which is defined as the following. Fx is 0 at all irrationals, and fx is equal to 1 by n when x is equal to m by n, and x is a rational, and m by n is in the particular form that the GCD of m and n is 1, and m and n are both integers. N is non-zero and all. In that case, we are at the point m by n, we are assigning 1 by n value to the function fx. And now my claim is that this function is continuous exactly on irrationals and discontinuous on the rationals. Okay. So can you see that why it is true? Just check on the rationals and irrationals separately. So first check at any rational point. So is 1 by n, but any neighborhood around that point will contain many irrationals, and so the value of the function at the irrationals will be 0. So it's not really continuous at any rational point, because at the point it is taking positive value, and no matter around it, there will be some 0 value of the function in their interval, because there are irrationals. And if you now look at the irrational, some irrational point, then the value of the function there is 0. And now any sequence, suppose the irrational point is, let's say, x. So any sequence xn converging to a, the xn can be made of rationals and it can be made of irrationals. If it's made of rationals, then it's always 0. And even if it's made of irrationals, then the value of the irrationals, that is, that denominator, must go infinitely large. And you have to prove that why that is true. So there are something you have to prove in between, but you will see that for a sequence of irrationals to converge to another irrational number, the denominator sequence must converge to infinity, like must diverge to infinity. So in that case, the 1 by n sequence, the value of the function will also go to 0, so the continuity is preserved at the points, at the irrational points. So this is a function which is continuous exactly on the irrationals and not continuous on the rationals. So you can construct a function like that. So then there is a, like, a very obvious extension of this question, that is, can we have a function from R to R which is continuous on rationals and discontinuous on irrationals? So we're just exactly turning the roles. Now this is a harder question to ask. Like, try to think of any example, try to construct a function which satisfies this, and that's really hard, like actually impossible to construct. Yeah, so you can just try to think about it and try to construct something. You will understand why it's difficult, but somehow you need to prove that there can't exist any function from R to R which is continuous exactly on rationals and discontinuous on the irrationals. Now, what we are doing? Okay, so what is the general formation of the question? So we have a metric space X and the distance function on it, D. Now, given a subset of X, let's say A, we are asking exactly this question, that do we have a function f from X to R exactly on A and not outside A? This is the general formation of the question we are asking, and now we are asking. So for A, and A is irrational, we have a function like that which is continuous exactly on A and not outside A. But when A is rational, the set of rational numbers, and again X is real, then my claim is you can't really construct a function which is continuous exactly on A. In this case, A is rationals and not outside A. So there are things to explore in this, like for what kind of subsets can we get a function which is continuous exactly on that subset and not outside that subset. Okay. Yeah, and then so now we are trying to characterize the sets which can appear as a set for some function from X to R. So now it's kind of the similar question, but we are asking from a more general perspective. So can we, given a set, can we directly say from this, looking at the set, that okay, we can construct a function from x to r which is continuous exactly on that subset of x, that is A, and not outside that subset of x? And like for what all subsets we can do that, and for what all subsets we can't do that. So in some way, on basis of this property, we are kind of characterizing the subsets of x. Yeah, so this is the answer we really want, that what subsets of x allow us to get a function which is continuous exactly on that subset. Okay. So to go on answering such questions, and again some more interesting versions of them, let's first build some basic machinery. I'm not really sure if you guys know about G delta and F sigma sets, so I will just define them quickly. So what is a G delta set? If X is a metric space, a subset of X is called a G delta set if it can be written as a countable intersection of open sets. So there are open sets in a metric space. You can define something as open set, like that. Of course, you have distance function, so you can know if some set is open and some set is not. And then if your subset can be written as a countable intersection of open sets, we call that subset to be G delta. And similarly, F sigma, those subsets which can be written as a countable union of closed sets. Now, just so that you can note, countable intersection of open sets might not be open, right? Countable union of open sets are always open, but countable intersection of open sets may or may not be open. Similarly, countable union of closed sets may or may not be closed. So let's just see a few properties of these G delta and F sigma sets to get comfortable with it. So firstly, clear. So it's very obvious that if A is G delta, then A complement is F sigma, because the intersection will, after operating the complement, it will get union, and the open set will get closed, and vice versa. So it's clear to see. And then any open set is G delta, and any closed set is F sigma. Clearly, a open set is just the intersection of that, like a single open set. It's a countable intersection of open sets, of course. Countable intersection of union. Now, it is also true that any closed set is G delta. Okay, so any closed set is F sigma, any open set is G delta. Again, any closed set is also G delta. Why is that true? You see, if A is a closed subset of X, then you can write A as the intersection of points in X as the distance between X and the set A is less than 1 by n, and the intersection you are taking for all values of n. So the points which will remain in the intersection are actually those points in the closed set, right? Trying to think why this is true is it's not very hard to observe. And then also observe that these sets, that X in X, such that distance between X and A is strictly less than 1 by n, is open for all n, right? Yeah. So we can write A as a countable intersection of closed sets. So any closed set is G delta. So any closed set is actually both G delta and F sigma. So a set can be both G delta and F sigma together. And basically all closed sets and all open sets are both G delta and F sigma. Okay. So just intuitively you can understand that most of the sets, like closed and open sets and all, they are both G delta and F sigma. So, but there are of course sets which are none of them, like they're neither G delta nor F sigma. Okay. You can understand, you can go on looking at different sets and trying to figure out if they're G delta and F sigma. Yeah. So, and these are the basic results we need to understand. Yeah. So what to do with all that? G delta, F sigma, what is the use of all that? Let's see. So let's now go back to the points of continuity. So again, we have a function from a metric space to another metric space, let's say. See, you can talk about continuity in general topological spaces too, but I'm restricting myself to metric space because I don't really know from what kind of background you guys are coming from. And of course, it's not uniform because you come from different universities and maybe different majors. So yeah. So let's see what continuity means. So by definition, if we say to be continuous at a point x naught in X, if for all epsilon greater than 0, there exists a delta greater than 0, such that the distance between, whenever the distance between x naught and x is less than delta, then the distance between fx naught and fx is less than epsilon in the other metric space y. Okay. So observe that it is equivalent to saying in many other different ways. So it can be formulated as f is said to be continuous at x naught in x if for all natural number n there exists an open set containing x naught such that f operating on that open set. So how does a function operate on open set? You are taking all those possible values, like f of u is just basically f of small u, where small u belongs to the set of all f of u's where u belong to capital U. Set, the function operating on this open set u containing x naught will be contained inside the a ball around f of x naught with radius 1 by n, and this is true for any n. So basically you were saying that for any arbitrary large values of n, the 1 by nth neighborhood around fx naught will contain some f of open interval containing x naught, and this is equivalent to the definition of continuity, what we know, or the general definition of continuity, and you can obviously check why they're equivalent. And again, just reformulating it, we can say that f is continuous at a point x naught in x if and only if for all natural numbers there exists an open set in x containing x naught such that the diameter of f of u is strictly less than 1 by n. Now, what is the diameter of a set? Diameter of a set is the supremum of all the distance, supremum of the distance between any 2 points of that set. Okay. So how far 2 points can be really within that set? That is kind of the diameter of that set. So the diameter of the function operating on an open set containing x naught should be arbitrarily small for different. We can get open sets containing x naught such that it is arbitrarily small. So that's the real issue. Okay, fair and nice. So now we know how to, like, when a function is continuous at a particular point, and we know several definitions of continuity. Very good. Okay, so now f to be this set of points where the function is continuous. So let a function operate from a metric space to another metric space, and then we define C of f to be all that small x in capital X such that f is continuous at x. Now we know when do we really say that f is continuous at x? We say it when there exists open set u such that the diameter of f of u is strictly less than 1 by natural number n. So we can write this C of f as this intersection over all the values of natural number of that all such points x in x such that there exists open set containing x such that the diameter of f of u is strictly less than 1 by n, right? And now when we're taking the intersection, the points left after all the countable intersection are basically those points for which it is true for all the values of n, and that is essentially those points at which the function is continuous. So this set of points of continuity can also be written like this intersection of these sets. And now what about this set? So let's just define On to be this set, the set of points in X, such that there exists the diameter of f of u is less than 1 by n. So if you define this to be On, then you have to. Now what I'm trying to say is, it turns out that this On are actually open sets. Okay, for all n, these ONs are open sets. In that case, you see, the CF, the set of points of continuity, is just countable intersection of open sets again. So that is what? That is G delta sets. Okay, so if we are able to prove that all these ONs are open, then we are basically able to prove that the set of points of continuity must be a G delta set. Okay, so that's something really good, really strong. We'll see why it's strong. It will help us to prove that there can't exist a function f from R to R which is continuous exactly on the rationals and discontinuous on the irrationals. Because we'll prove that the set of rationals are in R. Okay. So yeah, so basically we are trying to prove that from a metric space to a different metric space x and y, the set of points of continuity must be a G delta set. Yeah. So for that, what remains to prove is that On is always open, right? Okay. So this is our first result, and the theorem says that if x and y are metric spaces and if it's a function from x to y, then the set of points of continuity of that function f is a G delta set or a G delta subset of x more specifically. Yeah. So how to prove it? As I said, it's sufficient to prove that On is open for all n. And now how to prove a set is open? We have to prove it, right? We take any point x in On and then try to prove that x is an interior point of On. Now, as x is in On, there is open set U in x such that the diameter of f of U is less than 1 by n, and then U contains x, right? Then take just another point from that open set containing x, U. Let's say we take y. Then the diameter of f of U is still less than 1 by n, right? And U is also open set containing y. So y is also an element of On, because by definition On is a set of all elements for which we'll get an open set such that the diameter of f of U is less than 1 by n. Just recall the definition and see why this fits. And so we have x in U, and of course, so all the points are in On is an interior point of On, so we can conclude that On is open for all n. So now when On are open sets and C of f, the set of points of continuity of the function f, is just countable intersection of ONs. So it's a G delta subset of x. Okay. So now let's go back to our first initial problem. That is, can we have a function f from R to R which is continuous on rationals and discontinuous on the irrationals? The answer is no. To prove that we can't have any function from R to R which is continuous on irrationals, what do we really need to prove? We really need to prove that Q is not a G delta subset of R. Okay, so assume that Q is G delta. For the sake of contradiction, let's assume that Q is G delta. Then Q can be written as a countable intersection of open sets. Let's say the open set be On. Then take the complement both sides. That is the set of irrationals is just written as the countable union of On complement. Okay. Now this is the set of irrationals. So irrationals can be written as union of On complement. Now, so we just add the other rational numbers to it, and we get the whole R, right? So R can be written as the union of all the rational numbers, which is a countable union of singletons, right? Because rationals are countable. And again, union with the countable union of On complements where On are open sets. Also observe that On should be dense, because why should On be dense? Because Q is of On, so Q of course is a subset of each of these On, and Q is dense in R. So like if Q is dense and Q is subset of, must also be dense in R. So these ONs are open and dense sets in R. So the complement of them are nowhere dense sets. Okay, so what are nowhere dense sets? I will not really go into it, but there is something called the Beer category theorem. I don't know if you guys know this already, and which says that a weaker version of it says that R is a countable union of nowhere dense sets, which is impossible. So R cannot be written as a countable union of nowhere dense sets. But in this representation, we get R as a union of singletons of rationals, and again the union of On complements. The singletons are of course nowhere dense sets, and On complements are also nowhere dense sets. So R is written as a countable union of nowhere dense sets, but this is impossible because from Beer category theorem we know that is not possible. So Q is not a G delta set. So there's nothing to worry about if you don't really understand what Beer category theorem is or how this is proved, but at least you understand this, that whichever set is not a G delta set can't appear as a set of points of continuity for any function. That is something. And it turns out that Q is not G delta, and this is the proof of it. That's it. Okay. Now, there is another part, right? Let's see. What is that? Okay. So for now, we really understood to answer this like this direction of it, that if some set is appearing as a set of point function, then that set must be a G delta subset. That is something which we have proved, which we know. But now there is another direction to it. Given a G delta subset of X, can we construct a function which is continuous exactly on that subset? That is another question, right? Just let us go back to the first question we were asking, that can we construct a function f which is continuous exactly on rationals and not on irrationals? Now we can't do that because rationals are not G delta. But suppose you are given something which is G delta, a G delta subset of it. Let's say any countable set. Let's say the set, like that is easy to see, but let's say some G delta set which is not very easy to construct a function which is continuous exactly on the G delta set. But can we really say, given any G delta set, that we have a function which is continuous exactly on that set? We haven't proved that with, right? And unfortunately, it's not true. Given any G delta subset of X, we can't really get a function which is continuous exactly on that subset. But a very reasonable restriction on X can give us results like this. If we restrict X, like now we are treating any metric space X, but if we restrict it to something, then we will see, and the restriction is very intuitive, that why the restriction is needed. And then you will see that actually given any G delta subset of it, you can construct a function which is continuous exactly on the G delta subset. So remember that question you were asking about characterizing the sets based on the basis of this property. So then we can successfully characterize the sets which can appear as a set of points of continuity as G delta sets. So we'll go step by step and first see why this is not true in general. Okay. So metric spaces can have isolated points. Again, I don't really know if you guys know what isolated points are, but it's very easy to understand. Isolated point is something you can take some example like union the singleton set 3. So in this case, 3 is an isolated point. Which point is an isolated point? If there exists neighborhood around it, which intersection with that whole set is just that element of it, that particular, like no other intersection with it. So that is something which we call as. Suppose we have an isolated point. For example, in the set of naturals, all the points are isolated points, right? If you understand that intuition, we can go forward. And now, suppose we have a function from X to R, and X is a metric space with some isolated points. And let's say the set of isolated points be I. Okay. Then, do you see why the function is continuous at all the isolated points? A function is always continuous in isolated points because it's kind of the definition of continuity vacuously holds here. Because there is no point except the constant sequence of that point itself. And that is basically like X, and that of course satisfies the property of continuity, except that there is no sequence to check the continuity. So it's vacuously continuous at all the isolated points. Now, so if that is the case, then you see if we take a function from X to R, then the set of points of continuity, which we are writing as C of F, must contain all the isolated points of X. That is, if the set of isolated points is I, is denoted as I, then I must be a subset of CF. Okay? So in that case, there are some problem arising. Like in that case, we can't really say any G delta subset will get a function which is continuous exactly on the G delta subset and outside it. Because there, of course, there can be a G delta subset of X. In that case, it's obviously true that we can't get a function which is continuous exactly on the G delta subset and not continuous anywhere outside it, because it must be continuous on all the isolated points. Okay. So basically, we can, now this is not really a serious problem, because isolated points, you can just get rid of them and not think about the continuity, because they don't really say much about continuity. So we can concentrate on metric spaces without any isolated point. We can definitely do that, and those are called perfect metric spaces. Or we can, of course, and this also holds generally, like what result will prove now will generally hold for all the G delta subset containing all the isolated points. Okay, so in case of perfect metric spaces, we are going to prove that if so, we are starting with a metric space which has no isolated points, and then we'll prove that given any G delta subset of it, we can construct a function f from x to r, which is continuous exactly on the G delta subset and not outside it. Okay, and then we can extend the same result for general metric spaces with G delta subsets containing all the isolated points. It's just that little bit of restriction and some grading freedom to it. So it's not really something to pull your head off, but yeah. So after noting that, we can move forward with just considering perfect metric with no isolated points. So just to be clear, we haven't proved anything yet about always getting a function which is continuous exactly on that given subset, given G delta subset of x. See the proof of it. Now, so basically including the results we had before and the opposite direction of it, we will get the characterization theorem, which will say that let X be a metric space without isolated points, let A be a G delta set, then there exists a function X, there exists a function f from X to R such that C of f is equal to A. Okay, and this is the result we are going to prove, and then including this with the result we had before, we get this, that if X, and also going to the general step, if X is a metric space and let the set of isolated points of X be H, then now we are considering set of two sets in two different ways. Okay, so what we are really doing is we are taking all that which appear as set of points of continuity for some function defined on X, that is LHS. So this is a set of all subsets of X which appears as the set of points of continuity. And the RHS is all the G delta subsets of X which contains all the isolated points. So basically, sets in the left hand side are in the set of the right hand side, and like these are two same set of subsets. Okay, basically it's saying that a subset of X appearing as a set of points of continuity is equivalent to saying that it is a G delta subset of X containing all the isolated points of it. Now, forgetting about isolated points is just a G delta subset of X, and is not really doing much. Okay, so now we have to prove it. We have to prove the direction we are struggling upon, and that direction says, so the other direction is clear, what we really proved already. That is, if we have a set of points of continuity, then it must be G delta. Now, the other direction is, if we have a G delta subset, can we have a function which is continuous exactly on the G delta? Okay, so that is true for matrices without isolated points, but to prove that, we use this very strong lemma which says that if X is a metric space without isolated points, there is a dense subset in X for which its complement is also dense. For example, suppose in real, so real is a metric space without any isolated point in it. So you see rationals are dense in R, and the complement of rationals, that is irrationals, they are also dense in R. So this kind of thing will happen in any perfect metric space. Any metric space without isolated point will get a subset for which its complement is also dense in that metric space. Okay. Of course, there is a proof of it, but if we have time, the proof is really, there is no sophisticated, like there is no hi-fi stuff used here, but yeah, but the proof really, you have to think a lot to understand the proof now. So waiting in the waiting room, I guess. I can see another cursor moving on my screen. I don't really know whose cursor is this, but yeah, so Yeah, so let's just move on. So we'll not go through the proof now, but of course we can read the proof if we have time. Okay, so now we need to use this lemma in our proof. Okay, so what is the lemma saying again? The lemma is saying that if we have a point, then we really have a set, a subset of it, which is dense, which is complement also dense in the set X. Okay. So yeah, so how to prove it? So what we need to prove is, given a G delta subset of X, we need to construct a function from X to R, which is continuous exactly on that G delta subset, right? Okay. And yeah, so we take A to be a G delta subset, so it can be written as a countable union of countable intersection of open sets. Yeah. So now A complement is sets, right? So we write A complement countable union of Fn. And again, when you're writing union, we can just, with the loss of generality, like order F's in such a way and just do something such that the union is written in the form of Fn's where F so on, right? Yeah. And then, okay, we do this. After, so now we have to construct a function really, right? Okay. And also X is a matrix space without isolated point. So by the previous lemma, we have a subset B in X such that B and B complement both are dense in X, right? Okay. So now we define the function fx in the following way. We define fx to be gbx minus half times the sum of 1 over 2 power n, where n belongs to k, where k is the set of all natural numbers n for which x is in f of n. I can't really see my screen because of this cursor moving in my screen.
Okay, whoever is sharing the cursor S2, either it's me or Shayon, please move it.
Yeah, I think the person is also confused how to remove the cursor, but yeah, that will be helpful. I think you have to like someone who is in the moderator can, you know.
Okay.
My screen is visible, right?
It is to us, but can you just maybe restart the screen once? I think the
Okay,
cursor would be moved.
yeah, I will do that. Yeah, is it good now?
Yep, it is visible. Yes.
Okay. So
sorry, just happened a mistake actually, and then I'm not able to turn it off.
yeah. I understood that you were trying to turn it off. Yeah, no problem. Yeah.
Yep, it is okay. Now it's not there, so it's fine.
Yeah. So let's just continue. So what we are doing here is constructing a function. So let's just remember what we are trying to do here. We are trying to construct a function f which is continuous exactly on that subset of x which is given to us, which is a G delta subset. Okay. So we are given with A, which is a G delta set, f which is continuous exactly on A and not outside A. And we have this assumption on X that X is a symmetric space without isolated points. And so we also know that there exists a B subset of X for which B and B complement both are dense in X. Okay. Now we construct the function f, the required function, which is continuous exactly on A. How to construct the function? First what we do there? First we define a set K. Okay. So see, the way we wrote A complement is union of Fn where Fn are closed and in an increasing chain order, right? So now we define K to be the set of all indices for which X is in that Fn. So X is a point, right? X is a point in capital X. Now X can be in A complement, X may not be in A complement, right? Now, if x is in A, then x is not in A complement, and then x is not in any of this Fn, right? But now suppose if x is in A, sorry, if x is in A complement, then x is in some of these Fn, and if x is in F5 and x is not in F4, then the k is all the numbers from 5 onwards, right? Because it's subset, it's in increasing order, right? So as you can understand, this fx, this summation over all that n in k and of 1 over 2 power n will be 0 when x is not in A complement. Okay, so when x is in A, then this whole summation part will 0. Be not in A, then this summation part will converge to something, right? It will be something good, yeah. And now what about the other part of the function? The other part is gbx minus up. Now what is gbx? Gbx is the indicator function on B. What is that doing? If x is 1, if x is not in B, gbx is 0. So gbx minus half. If x is in B, this is minus half, and if x is in not if x is in B, it is half, and if x is not in B, then it's minus half. The use of this part of this function is just to change sign depending on if x is in B and if x is not in B. Okay. So now my claim is that this function is constructed in the following way, that one part of the function is determining the value of the things if it is in B and not in B, and the other part of the function is determining if it is in A. If it is in A, then the other part is 0, then the whole functional value is 0 if the x is in A, and if it's not in A, then it's doing something. So we'll see what it is doing. Then we'll try to prove that this function fx is continuous exactly on the G delta subset A and not outside A. Okay, so let's see how to prove it. So as we observe that fx is equal to 0 whenever x is in A, right? Now we have to prove, so first we want to prove that it is continuous at all the points in A. Okay, so now suppose xn is a sequence which converges to x, then fxn also converges to 0. We have to prove this because fx is 0. Now why does fxn converges to 0? See, firstly, this xn converging to x can come from both A and A complement. If it is coming from A, then fxn is already 0, so nothing to worry about. Now, if xn is converging to x, but xn is coming from A complement, then what is happening? Now, let's see. A complement, we wrote A complement as a countable union of closed sets and in an increasing chain order, right? But all these closed sets are there, right? So x can't be a limit point of any fixed fk because they are closed set, and x is in A. Again, x is in A, so x is not in A complement. So x is not in any of these f's, the closed sets, fk's. Now, if x is not in any of the closed sets, then it can't be any of the limit points because they are closed, right? So this fxn, if xn is converging to x and xn is coming from A complement, they can't really come from a single fk or stop coming from after a particular finite stop in fk. So it must go on for large values of k, right? Because if it stops there, then the limit point should be there itself, but the limit point is not in A. Okay, I hope I'm clear here. If there is any doubt, you can let me know. But yeah, so the thing you have to understand here is, if xn is converging to x when x is coming from A, then even if xn is coming, it must come from different fk's, you know. And in that case, when the k is increasing, you see what happens to the function. Okay, so in that case, so the limit is again coming to 0, right? Because if the k is large, then the other part of the function is also getting close to 0. Okay, and the closer we get to x, and the functional value is getting close to 0, and fx is also 0, so the function is continuous at any point in A. So whenever x is in A, we get fx to be 0, and even the sequence f of xn is converging to 0 if xn is converging to x. So by the definition of continuity, the function is continuous at all the points of A, right? So now again we have to prove that it is not continuous at any point except in A. Okay. So now let x is okay. So now suppose x is not in A. So x is in A complement, right? So we are taking two cases. First, if x is in A interior of the A complement. So suppose x is in interior of the A complement, then you have to see that every neighborhood of x will contain points taking different signs of x, signs of f, right? Because both B and B complement are dense. Now we are using this B thing, okay? So again, go back to B and B complement and the definition of function. So now we are looking at a point which is in A complement. 0. And in any interval around it, there is a dense and there is B and B complement. There are points from both B and B complement. And at the points of B, the function is taking negative value. In the points of A, the function is taking positive value. And why the interior is important? Because all the points are in A complement. So all are non-zero points. The value are all non-zero. So, but some of them are positive and some of them are negative. And this is true for all neighborhood around it, right? But the functional value is either positive or negative. It can't be both. So in any way, it is not continuous if x is in some interior of A complement. So for any interior point of A complement, the function is not continuous at that point. That's clear. Because of the different signs. A complement, but not in interior point of A complement. If it is not an interior point, there exists a sequence coming from A converging to x, right? And then the functional value of the points of the sequence are always 0. So there is a functional sequence of zeros converging to f of x. But like it should converge to f of x. But again, f of x is non-zero, so it can't happen. So again, if x is not an interior point but is a point in A complement, then the function can't be continuous there by the construction of the function. So we have proved that the function is continuous exactly on A and not outside A. Okay. So we have proved that C of f is equal to A, exactly equal to A. We started again to just brief out what we did. We started with a given G delta subset of x, and x is a matrix space with isolated points. We successfully constructed a function which is continuous exactly on A and not outside A. That's good. Okay. So now we have proved that given any G delta subset, we can get a function which is continuous exactly on that G delta subset. So we got our characterization theorems, and we also got the final one, including the former result with the later one. So if there is any comments or any doubts regarding whatever we discussed so far, it might be a good idea to unmute yourself and let me know. Okay. So now we really have a strong foundation on the set of points of continuity. We really know everything about it. We know which sets can occur as a set of points of continuity. We know that for which sets we can construct a function which is a function with that exactly set of points of continuity, and so on. And as you see, this G delta sets plays a very important role in our discussion. Yeah. I think we have some time left, so we'll go on to another interesting part of such discussion, that is continuous and discontinuous extensions. So till now we are just talking about functions, a particular fixed function from a particular domain to a particular codomain. Okay. Some of you might be asking that why we are always restricting the codomain to R. So that is, see, when we are talking about the thing is, the important part is the domain of it. There can be some very technical, but yeah, it doesn't depend much on the codomain on it. But yeah, but of course there can be codomain where these statements are not true. Trivially, there can be codomain where the statements are not true. But yeah, so we will restrict to R because almost all of the properties of continuous functions will be mainly on the structure of the subsets, the set of points of continuity of the domain and how they behave and how they can extend them to. So that is a part of the discussion we are coming to now. So let X be a metric space and let A be a subset of X. Now suppose you are given a function from A to R, which is continuous. So you are first given a function from a subset of X, not from the whole X. And now you want to continuously extend the function to the whole codomain X. So what do I mean by that? I mean by that is we have to construct a function g from X to R such that it is continuous on X and its restriction on A, that subset, is equal to G. Like, by that what I mean is, if take a point in the subset, suppose A, small a is in capital A, then G of that is G is consistent with F. Now we extend some points. So you can think G as of the function F itself, but now we are also giving values, functional values to the other points in X, rather than just giving functional values to A. So we're just extending the function. Okay. So now we can extend the function in a continuous manner. In that case, what we are doing in the points we are adding functional values to, we are making sure that all the points we are adding the functional values to are still continuous. So that is a continuous extension. You are extending the function in a continuous way, such that the extension function is also a continuous function, right? So that is the thing, and it is really important for our study in various topological and metric space things. Yeah, and now we'll define something as maximally discontinuous extension. This is the particular type of extension we are interested in. Okay. So what is that? Let X be a metric space and let A be a subset of X. Now we are given with a function from A to R at first, which is continuous. We want to extend the function to whole of X in such a way that it remains continuous exactly on A and not outside A. Like we're extending the function, but we are not letting it to be continuous at anywhere except the places it were already continuous, right? So we're doing exactly the opposite of what we did in continuous extension in some sort of sense. Okay. So in this case, we call G to be a maximally discontinuous extension of F. We are extending F from a subset of X. The domain of F was a subset of X, that is A, and F was completely continuous. Now we extend F to the whole domain X, but make exactly on that A it was continuous before, and is not continuous at anywhere except A in the extended function. Okay, so that is when we call a function to be maximally discontinuous, and in that case we call F to be maximally discontinuously extendable. Okay, and G to be the maximally discontinuous extension of F. So take some time to get used to these definitions. Just maybe I will drink some water, and then we will continue. Okay, so we have a very famous theorem for continuous extensions. So it says that let X be a metric space and let C be a closed subset of X. Then, given a continuous function from C to R, from the closed subset to R, we can extend that continuous function continuously to the whole set X. That is, if X is a metric space and C is a closed subset of X, then any continuous function from C to R is continuously extendable. We can extend the function to get a capital F from X to R, which is continuous on the whole X and which is consistent with F on the set C, on the closed subset of X, C. Okay, so that's great. Now we want to see for which all subsets we can discontinue. So this is theorem. These all subsets and such functions from these subsets, you will get a continuous extension of it. So these kind of functions are continuously extendable when the domain is this kind of particular subsets of X, in this case closed. Okay. So another question to ask is, because we did so much with G delta, of being closed with just doing g delta. So that is, can we say that given any g delta subset of x and a continuous function from that g delta subset of x to R, we can extend continuously to the whole set x? Can we say that? The answer is no. We can't do it for open sets, okay? And open sets are also g delta. For example, you can take the counter example, if from 0, 1 to R, and define it continuously as f x equal to 1 by x, 0, 1 open. So now small f is a continuous function, but it can't be continuously extended to R. Like you can't get a function g from whole R to R, which is continuous and which is also consistent with, like g for which g of x is equal to 1 by x for all x between 0 and 1. You can't get it because of course you can't define it at the point 0. So anyway, so these are trivial counterexamples. So the thing is that we can't really improve the Tietze extension theorem very much. Okay, that's the theorem. It's for closed sets. If a function is continuous on closed set, then we can continuously extend it. That's it. Now, what can we talk about? What can we think about discontinuous extensions? Okay. So now what do we try? What we are trying to do? We are trying to do this. Given a G delta subset A of a metric space X containing all isolated points, a continuous function f from A to R. So we have a G delta subset A of a metric space X, and we have a continuous function from A to R. And of course, if we have a continuous function from A to R, then A must be a G delta subset and it must contain all the isolated points. That is also something we proved. So now suppose you're given a G delta subset containing all isolated points and a function which is continuous from A to R. Then is there a function from G x to R such that G is a discontinuous extension, is a maximally discontinuous extension of f? That is, this G is continuous exactly on A and not outside A, and its restriction to A is f. Okay, so that is our question. That is the problem we are tackling with. And as you can see, it's a stronger version of something we already know. If we prove this, then we can of course construct function which is continuous exactly on some G delta set. We already constructed a function assuming a strong lemma and did all that. That given a G delta set of a perfect metric space, we're trying to construct a function continuous exactly on that G delta subset. But now if we prove this, then it's much stronger. We can not only construct it, we can construct it in kind of with much more flexibility, because we can construct it by extending it from any continuous function. Any type of function, any kind of value you want to put in a continuous function, after that you try to extend it, you can also extend it and make it continuous exactly on that G delta subset of it. So it's really a very strong, very strong result, and we want to prove it. Okay. And what we did already is we already did it for f(x) equal to 0 for all x. Observe what we did is just a better analogy of it. You see, we already constructed a function which is exactly continuous on A and not outside A, and at A the function was exactly equal to 0 the way we constructed it, right? But now we are saying that we can construct it in very different ways, and that even someone else telling me how to construct it, like someone else is giving me a function and the functional values at A, we can extend it all over X in such a way it's just continuous exactly on A. Okay, so that's really strong. Let us see how to prove it. Okay. So again, we'll restrict ourselves to perfect metric space. It doesn't really make sense to do it over general metric space. It's whatever result you have for perfect metric space, it can be easily extended to general metric space by just including the set of isolated points in the set of points of continuity in some way. Okay, so yeah, so there are 3 steps. I don't think I will have time to go over all the steps in very detailed manner, because it's, yeah, so the proof, as the stronger the result gets, the difficult the proof is, of course. Not always true, but in general, yeah. So we'll do it in the following 3 steps. First, we'll try to prove that given a closed subset of A and a continuous function from A to R, there exists a function G which is continuous exactly on A and restriction of A is F. That is, for closed subsets and continuous function from A to R, F is discontinuously extendable. For closed subsets, F is continuously extendable, that is Tietze extension. We are saying for closed subsets, it's also discontinuously extendable, and that we will prove. Okay. After proving that, we can prove that for dense G delta subset, it's also discontinuously extendable. Okay. And then we can prove in most generality that for any G delta subset, a function from A to R is basically discontinuously extendable, maximally discontinuously extendable. So you may of course ask that why we are not proving step 3 directly, and the obvious answer is because we need step 1 and step 2 to prove step 3. Of course, step 3 implies the statement of the third statement implies the second statement. Do it like I think so. Yeah. So G delta set and dense. So of course, so the last statement is the strongest of the following, but we need to go step by step and see how it is proved. So for a closed set, so suppose A is a closed set. Now we have a function from A to R which is continuous. Now by Tietze extension theorem, we can have continuous extension of f, right? That is G1 from say x to R. That's very easy. Again, we can have a function G2 from x to R such that G2x is equal to 0 for all x in A, and C of G2 is A, like it's continuous exactly on A. Why can we have that? From the way we proved, from the proof of the state G delta set, we can construct a function which is continuous exactly on the G delta set. How did you construct a function? The way we proved it, and from the construction, all the points at A is 0. The value of the functional values of all the points at A, we made the functional values to be 0. We constructed it in such a way. So you can do the same construction here and get a function G2 which is 0 at all A and continuous exactly on A, right? Because closed is G delta, and there we had for any G delta. Okay. So now we define a function G to be G1 plus G2. What is G1? G1 is the continuous extension of f. What is G2? G2 is a function which is continuous exactly on A, not outside A, and G2x is equal to 0 for all x in A. So now, as you can see, that G2 is 0 in A, we can say that Gx is equal to G1x equal to fx. So G is also an extension of f, right? And it's also easy to see that G is continuous exactly on A. Why is G continuous exactly on A? Because G1 is continuous all over X, and G2 is continuous exactly on A and not outside A, and G is taking the value 0 at A. So, okay, you can easily check that it's continuous exactly on A, not outside A, and it's also an extension of F. So, given any continuous function from A to R, whenever A is a closed set, we can maximally discontinuously extend the function all over the set X. Okay. Now, step 2. Now we are trying to prove it for in general dense G delta sets. Okay. So how to prove it? So suppose A is a dense G delta subset of X, and we have a continuous function f from A to R. We want to maximally discontinuously extend the function f. So now A is G delta, so A complement is f sigma. So A complement can be written as countable union of disjoint closed sets. In the same way, we write it like this. Okay, in the increasing chain order. Okay, and now we can make them disjoint also, right? In writing like this, and then we can take f1, then f2 minus f1, and f3 minus f2, and so on, and that will make it disjoint. So A complement is written as countable union of disjoint closed sets, right? Now we define k of x equal to n if x is in Cn. So if x is in A complement, x is in exactly one of these Cn. So k of x is defined to be n. Okay. If x is in Cn, it's easy to see that xn is a sequence in A complement converging to a point in A. Then k of xn is equal to is diverging. It's getting very large, right? From the same argument we did in the proof of the theorem we did before. And now what we do is, when A is dense in A, we can talk about the limit of any point B in A complement from taking points in X converging to that point B in A complement. Okay, this limit may or may not exist, of course, but what we can actually do is we can take sequences from A converging to B. That's what you can do. Okay, so now we define B1 and B2 subsets of B in such a way, like if the limit exists, then we take the b to be in b1. If the limit doesn't exist, we take to be in b2. So now you have to see that f can be continuously extendable to a union b1 by just defining the limit to be the. We are trying to basically do here. Let's go back to the thing what we had. We have already a function which is defined over a, and which is continuous. We want to define the function over all x. So we want to have to define the function over points which are not in a but which are in x. That is exactly the points in b. So you have to somehow define functional values at the points in b, and you have to do it in such a way that it is not continuous anywhere outside it. Okay. So yeah, so we'll do that. And so how we are doing that? We are taking f of b to be the, of course, the limit of fx and whatever we can take. And since a is dense in x, for each x in a complement, we can choose a point ax in a such that distance between x and x is less than 1 by kx, right? Because again, it's dense in x. And now we define a function h from a complement to r by hx equal to ax. Okay. It might get a little complicated here. So let's just see that what is our function g, the final function g from x to r, which by our claim should be continuous exactly on a and not outside a. Okay. And that should be a discontinuous extension of f. So it should be taking the same values as fx at x. So fx, when x is in b1, we define the function to be fx plus 1 by kx, 1 over kx. See, fx is the limit, the limiting thing from the how we define the limit, how we define extended fb. So at b1, we are doing fx plus 1 by kx. Now this 1 by kx, whenever x is not in a, in x is in a complement, this 1 over kx is something non-zero, right? Okay, so we'll see that what's happening. And then f of hx, and this 1 by kx is going to 0 whenever x is going to somewhere near a, right? So see the way we, now f of hx, what is hx? hx is equal to ax. And what is ax? Ax is a point in a which is very close to x in b2, right? So kind of we are at, when x is in b2, we are defining function to take the values very near to b but in a. Okay. So we can check. So I will suggest you to go over and check that at points of x, you see, or any of the functional sequence will also converge to fx, because 1 by kx will get very close to 0 and hx will get very close to x, okay, whenever we take a sequence from b2 to x. And from the other part, we consider it in such a way that it is not continuous anywhere outside fx. Okay, so yeah, so in such a way, so we do it for dense G delta set. We prove that it is continuously, maximally discontinuously extendable. Okay. And now the final step, we do it for any general G delta set. So you see how we use the closed thing here, right? So, and here you will use both the dense and the closed thing, the previous two steps for the step 3. So what you will do is just let A be a general G delta set. Then you take B to be a closure minus A. That is the limit points of A which are not already in A. Okay. That A is a closed subset of X minus B. Okay. So why is A a closed subset of X minus B? Because all the limit points which are not in A, we are removing it from already from the whole set. So all the limit points of A which are in X are already in A. So it's a closed set in X minus B. Now by case 1, f can be extended to a function from x minus b to r, right? Because A is closed in x minus b. So f can be extended to x minus b to r, discontinuously extendable, such that the function is an extension of it and also is discontinuous exactly on A. Also, you see that A is a G delta subset and which is dense in A closure in the subspace topology, right? So by case 3, sorry, so it should be step 2, but yeah, whatever. So we can extend a function from, we can get a function h from A closure to R, which is again a discontinuous, maximally discontinuous extension, right? So see, so we needed to define the function everywhere outside A. So we defined it at all the limit points of A, which are not in A. Okay. So we are defining into other points of A, like x minus, like which are not in the closure of A. We're defining that by gx, and we are defining in the closure of A by hx. So we are basically defining in the whole set X, right? And see, this consists because hs is equal to fx, small fx at x equal to s. It's consistent with f, and it's also a maximally discontinuous extension because we use this to complemented to maximally discontinuous extension, and the set of points of continuity in both cases is just exactly equal to A. Okay. So that is basically the sketch of the proof, and now we have the complete proof, and we say, so okay, so there is a name of this property, it's called discontinuous extension property. So a topological space, I will coin it in topological spaces only because it's more important there. So x tau be a topological. If each function f from A to R on a G delta subset A has a discontinuous extension, then that topological space is called a DEP space. Okay, and what we really proved now is perfect metric spaces are DEP spaces. Okay. And this is actually a very strong result, and it's stronger than whatever we proved before in the other direction of our set of points of continuity thing. Okay, that not all perfect topological spaces are DEP spaces. We have counterexamples in perfect separable Hausdorff spaces itself. So that, okay, so just to summarize what we had so far, we are able to continuity or the set which can appear as set of points of continuity for any function from a metric space to R. We are also able to see that how a function from a particular subset of a set can be discontinuously extendable in such a way that it is not continuous anywhere outside it, and for which all sets and which all functions we can do that. And perfect metric space is a space where we can do that, so it's a DEP space. So yeah, so we have fairly almost the complete picture of set of point of continuity and how continuous and discontinuous extensions work. So I think that's it. That is all I had to present, and I think we can move on to the Q&A session.
Okay, so thank you, Soham. Now for the question answer session. Hopefully you guys enjoyed the talk. Now feel free to ask your questions. You can unmute yourself.
Questions, then yeah, so it's, and I hope you all are enjoying this limit camp, because yeah, you guys really should like take the most out of it, and I'm sure the organizers and Snehin and all are doing a great work, and thanks for inviting me for the talk.
Bakshi, it has been a wonderful talk, and I'm sure everybody enjoyed it. So
Yeah.
Do you have anything else which you would like to discuss? Because we have some time.
There is nothing really left to discuss here, but what I will do is, so there is that proof of that wonderful lemma, and such lemmas and all the theorems we did in the slides, the theorems which are in the slides are really important in many different aspects of analysis and topology. So I will share the slides maybe with them, so they can go through the proof, and after that, if they have any doubt, and even if there is a late comment or something which you are not having in mind now, you can of course let me know through them, or you can directly mail me. I will write my mail ID here. So that's something you guys can do. And
yes,
I think
that,
yeah.
And anything else? So
I think that's it. We can call this a day.
okay, then let's. Thank you very much, Soham, and we'll stop this meeting now. So your next meeting would be from